Now, you've learned since middle school what phase changes are, right? Things melt, things boil, condensation, evaporation, all of those things, right? So I know you know that the melting point is the temperature at which particles start to go from solid to liquid. They start to move apart a little bit. Those intermolecular forces get a little bit weaker and they can flow, they can move more. You're putting energy in, so those particles have a little bit more energy. So melting point is going to be very similar to boiling point. These stronger intermolecular forces, the higher the melting point is going to be. You'll see HF, NH3, and H2O still have abnormally high melting points, and everything else kind of increases across the period. So these are all of the phase changes you need to know. I know you know melting, vaporizing. The other way is condensation and freezing. The ones you might not remember, might not be familiar with or as familiar with are sublimation, which is going straight from solid to gas. That's what dry ice does when it just sits out. It goes straight from solid to gas. That's sublimation. And getting it to go the other way, which is kind of difficult, is called deposition. So like it deposits back onto the solid. That's why it's called deposition. Okay. Over here, you'll see your melting point. We have a bunch of different substances and a bunch of different melting points. And the things with the higher melting points, so like this is an ionic compound, and everything has dispersion forces or London dispersion forces. But ionic compounds obviously have super high melting points because in order to melt an ionic compound, you have to actually break that ionic bond. Whereas all covalent substances, all you're doing is spreading those molecules out. You're not actually breaking bonds. So then we're looking at the rest of the intermolecular forces. So F2, super low boiling point, right? This is a non-polar molecule. It only has London dispersion forces or melting point, sorry. We'll look at fructose has, compared to the other ones, a decently high melting point, but it has dispersion, dipole-dipole, and hydrogen bonding. So when we're looking at melting points, it goes ionic, has super high melting points. And then for the covalent substances, if they have hydrogen bonding, and then it'll go dipole-dipole, and then it'll go just dispersion forces. So based on those intermolecular forces. Okay, so these are, again, the ones that you need to know. If I were to write these phase changes or physical changes into chemical equations, remember, we're not breaking any bonds in a physical change. You're just, H2O is going from liquid to solid. That would be freezing or melting. And we will actually use the term fusion. You kind of think of ice is going to, yeah, I know it's not a good word for it, but melting or fusion of ice is going from solid to liquid. So these two are opposite of each other. They both occur at 0 degrees Celsius. It just depends on if you're cooling or heating. Evaporation or vaporization is the term we will be using, is from liquid to gas. Condensation is from gas to liquid, and these both happen at 100 degrees Celsius for water. And then our new maybe to you ones are sublimation and deposition. Like I said, I used carbon dioxide or dry ice as an example because that's one that most of us have seen happen, goes from CO2 solid to CO2 gas. Or deposition, we can make it go the other way, right? And so I just wrote an equation for deposition of water, which it's kind of hard to do. So there is energy associated with these phase changes. Okay, and what we're going to call that energy is the heat or the enthalpy, right? Energy, enthalpy. We already did a whole unit on this of vaporization. That would be like the energy required to vaporize something. Okay, the amount of heat required to vaporize a substance. So it's going to be like, I'm either going to give you it in kilojoules per mole or kilojoules per gram. So if I say I have 100 grams of water, I'll be like, how much energy would it take to vaporize that? And we'll be able to calculate that actually pretty easily. We will also have the enthalpy of fusion, or the amount of energy needed to melt it. So we'll have vaporization and fusion, or the amount of heat required to melt a substance. Again, will be in kilojoules per mole or kilojoules per gram. Now, that being said, the exact reverse process would require the exact same amount of energy. We would just have to take the energy out. So we could use heat of vaporization to figure out how much energy we would have to remove to condense something, or we could use delta H of fusion to calculate how much heat we would have to remove to freeze something. So we just call them all, this is delta H vaporization and delta H fusion. Every substance has its own specific enthalpy of vaporization and enthalpy of fusion. So I am going to show you how to use those and how to figure out the energy required to melt, vaporize, freeze, condense things. So what you're looking at here is what's called a heating and cooling curve. And yes, I know it's not curved, but you have lines essentially. And it's not just a straight line. And what this is a graph of is energy. So we're putting energy into it. As we increase the energy, we're going to be heating a substance up, right? So say we start with some really cold ice, like -10 or something like that. We'll call this -10. You're going to heat it up until it gets to 0 degrees Celsius, and then it's going to melt, right? As we're heating it up, it's going to melt. And whether you know this or not, it actually is going to stay at 0 degrees Celsius until it's completely melted. Because in that process, what we're doing is we are using our delta H fusion, we're melting it. We are using the energy to melt it, not to change the temperature. So here we're changing the temperature till it gets to 0, and then it'll phase change. And then once it's all turned to liquid, then it'll start to heat up again up till it gets to 100, and then it'll all vaporize, and then we can get vapor to actually get very, very hot. This is why when you open like your hood of your car, if it's steaming, that steam can be way more than 100 degrees Celsius and can burn your face very, very badly, is because steam can actually get a lot hotter than 100 degrees Celsius. And so this is a heating and cooling curve. These specific temperatures are for water, but they could be different temperatures for any other type of substances. So as we go to the right on this curve, we are heating it up and undergoing our phase changes. If you were to go to the left, then that would be cooling it down. Those are the phase changes it would undergo. So anytime I'm trying to give you a problem where I'm like, how much energy would it take to blah, 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 you're going to have to figure out, well, what phase changes are going on and what's the temperature changes that are going on. Technically, you could have a 5-part thing. If I gave you ice at -10 and I want you to get it all the way to vapor at 110 degrees Celsius, you can have to do 5 calculations. The calculation to heat it, to melt it, to heat it, to vaporize it, and to heat it again. So these can be kind of long ones, all right? So you got to read carefully, and I would draw one of these heating and cooling curves before you actually get into it. Okay? And in case you were wondering, the enthalpy of sublimation is actually just enthalpy of fusion and the enthalpy of vaporization together, because you're just doing both at the same time. Okay? So I'm going to show you how to use this. These are the calculations. I'm going to give you the constants, and then I'm going to walk through a couple of these with you. So this is a better representation of the heating and cooling curve for water. It's got everything marked on it, essentially. From A to B, that's where it's ice and you're heating up. B to C, you have a mixture of ice and liquid water until it is all liquid. And then it'll heat up again to 100, and then you have a mixture of liquid and vapor until it all vaporizes, and then you can heat up the water vapor. So for each section, you actually have a different calculation that you would have to do to figure out the amount of energy. One we used a long time ago, back in like module 5, was when we're changing the temperature of something, you use Q equals MC delta T. So if I'm heating up a piece of ice, I would do the mass of the ice times the C for ice, which is not the same as the C for liquid water, unfortunately, times the delta T for ice. So that's a temperature change. Now, unfortunately, since while we are melting it, you don't actually have a temperature change. You can't use Q equals MC delta T, because yes, it does require energy to melt it, but we don't have a temperature change, so it's not 0. So the only thing you have to do to calculate at a phase change is to do Q equals M times the delta H of fusion. So the mass times the delta H of fusion, which is a number, a constant that I also have to give you. It's just easier to calculate than the other one because there's no temperature change. Okay, so for phase change, you just do the mass times delta H fusion. And then I would have a temperature change again. So you would do Q equals MC delta T using the C of water, which is 4.184 joules per gram degree Celsius. And then D to E, you would have another phase change. So it's just the mass times the delta H vaporization this time. And E to F would be another Q equals MC delta T. So again, I would draw this out for whatever substance you're doing a calculation for. Any slants are Q equals MC delta T, and any flat lines or phase changes are Q equals M times delta H. Okay, now the constants for water are ones I'll give you on your equation sheet. The delta H fusion for water is 6.01 kilojoules per mole if it's in moles, or 334 joules per gram if you get it in grams. Delta H vaporization for water is 40.67 or 2,258. Now you'll notice it takes a lot more energy to vaporize water than it does to melt water, which if you think about it, kind of makes sense because it's hard to get all those molecules spread far enough apart to turn into a gas. So almost always for substances is your delta H vaporization bigger than your delta H diffusion. And then I gave you the C values. Remember, I told you the C values aren't the same for water, ice, and steam. It's actually the hardest to heat up water because of the hydrogen bonding. And it's a little bit easier to heat up ice, which is 2.1, or to heat up steam, which is 2.0. Okay, so we're going to go through some calculations together on this one. Okay, so questions like this are going to take some careful reading. So this is what we're going to do. I need to get my pen. Okay, so it says what quantity of heat. So I'm going to break this down. All right, I want quantity of heat. Heat is energy, so I either want joules or kilojoules or calories or whatever. Okay, all of those are heat quantities. Is required to convert. I have 55 grams of water, so this is a mass at 25 degrees Celsius. So I just said water, so that would be liquid water at 25 degrees Celsius. We also know it's liquid because it's between 0 and 100. So this is my starting temperature. So this is my TI. To water vapor at 100 degrees Celsius. So this would be my TF. Now, if you were just reading this, you might be like, well, I got a TI and a TF, so it's Q equals MC delta T equation. Well, yes, but is there a phase change? Yes, because I want to know from liquid to water vapor, which is gas. So there is a phase change. Now, this is why I recommend you draw the little graph first. Okay, water, looks like this for every substance. Now, where are we at? 25 degrees Celsius is liquid. This is where my liquid is. So I'm somewhere right there. Okay, we'll call that one 25 degrees Celsius. So I'm going to have to heat it up to what temperature? Well, we boil at 100 degrees Celsius. Okay, and that's where I'm ending, except that I also want to vaporize it. So I'm going to have to go from here to here as well, still at 100 degrees Celsius, but I'm going to have to go from liquid to gas. So there are two sections to this calculation. I have from A to B and from B to C. These are going to be my two calculations that I'm going to have to add together to get the total energy to convert 55 grams of water at 25 degrees Celsius to water vapor at 100 degrees Celsius. Okay, so I'm going to do from points A to B first. I'm just labeling them that way, just hopefully you can follow along here. So from 25 degrees Celsius to 100 degrees Celsius. So this is just going to be a Q equals MC delta T, because I'm just doing my temperature change. So Q equals M, I have 55 grams, times C. The C for water is 4.184 joules per gram degrees Celsius. They're both in grams, so I'm good, that matches. And I'm going from 100 to 25 degrees Celsius, so that's 75 degrees Celsius is my delta T. You'll notice all my units here will work out. This would spit it out in joules. So the amount of energy required to heat it, just heat it, from 25 to 100 is 17259 joules. I'm not rounding yet because I'm not done. All right, that's for the heating part. Now the melting part from B to C would be a Q equals M delta H because it's a phase change. All right, so I would be like, all right, well, that is 55 grams. Now I need the delta H. Now, am I fusing it or am I vaporizing it? I'm going from liquid to gas, so I'm vaporizing. So I need the delta H vaporization of water. So let's look up here, delta H vaporization. I'm in grams. I don't really want to convert to moles. So I'm going to use this value, 2258 joules per gram. So I got 2258 joules per gram. So this, to vaporize 55 grams of water with no temperature change, is 124,190 joules. So the whole process is going to be this number plus this number. Okay, so the total equals 17259 joules plus 124,190 joules. As it takes a lot more energy to do the phase change. And so that is 141,449 joules. Now it's a really big number, so I'm going to go ahead and put it into kilojoules. It didn't ask you to, you don't have to. So if you just divide by 1,000, and let's see, I need like two significant figures. So that would be 140 kilojoules. That is how much energy I need to heat a sample of water at 25 degrees Celsius to 100 and to vaporize it. So again, check if you have a phase change and temperature change. So I would like you to try example number 4 by yourself and check your answer. Okay, so you'll notice I labeled this one as kind of an extra credit question because it's kind of 2 parts. We got a problem solving thing going on. So it said, what's mass of Freon? This is stuff that can cool down hot things like your refrigerator, must evaporate. Okay, so I'm going to evaporate this thing and I'm going to use the energy put in to evaporate that to freeze water because I have to take the energy out of the water. So I'm going to use it to evaporate the Freon. This is what's going on in your refrigerator. At 22 degrees Celsius. The heat of vaporization of Freon is this. So what we're going to do is we're going to figure out how much energy I need to take out of the water to get it to freeze. And then I'm going to put that energy in because, right, it has to go somewhere to the Freon and see how much Freon I need. So what's going on here is I did step 1 over here, water. I figured out how much energy I need to get it to 0 degrees Celsius and then freeze it. And that is in total 10,651.2 joules. And then I use that number over here as the Q for Freon. I'm going to put it into the Freon. I need to know what mass, and this is its delta H because all I'm doing is evaporating it. And the mass is 37 grams. Again, this is kind of like an extra credit question because you really got to think about it.